Tabak and Business Development Manager for Specialties at Envalior. Today, we will talk about the recent need that has emerged in the market to have PTFE solutions available. In particular, we will walk you through the tribology field, where until now, PTFE has been broadly used as an enabler to reduce friction in high-demanding wear and friction applications. However, today, PTFE is being questioned and threatened due to a possible ban in both its use and its manufacturing. At Envalior, we are closely monitoring market trends and our customer needs, and hence we are dedicating efforts to provide PTFE-free solutions, in our case, with main focus in tribology applications. Tribology is the science that explores the interaction of surfaces in relative motion, a complex topic from which sometimes it is considered as much as a science and as an art. Typically, tribological applications can be very broad. One can cluster them in three main industries, going from mobility, which includes automotive and two-wheelers, to consumer goods and robotics. Efficiency and durability are key requirements in tribology. From an efficiency perspective, industries are looking for ways to reduce loss of energy due to the frictional heat generated when the application is in operating, always with the ultimate goal in mind of lowering power consumption, while from durability perspective, wear needs to be controlled to get the desired durability. Otherwise, part surfaces are worn out, which can result in expensive downtimes and in shortened product lifetime. Here is where material choice must be done very carefully, and when it comes to tribology performance, material selection has a direct impact on the overall application reliability, as well as in the application design. We can mention three representative tribology applications: components, gears, bushings, and guide chains. Having a closer look at the requirement needs in the final application, one can typically find the following needs: low friction and low wear, which can be considered as the more relevant in this field; high temperature resistance; low weight; low noise, which nowadays is receiving an increasing attention; and not to forget the need of having cost-effective solutions combined, if possible, with friendly solutions. Either method of plastics can be chosen carefully with the ultimate purpose of fulfilling the application requirements. The range of suitable plastic materials extends from POM, PEEK to polyamides, this later including PA66, PA46, or PPAs. Nowadays, for demanding wear and friction applications, it is a common practice to make up use of PTFE. PTFE, which stands for polytetrafluoroethylene, can be used either as pure polymer for certain applications, such as seals, surface treatments, non-sticky cooking pans and pots, firefighting foams, and medical industry, amongst others, or in powder form in polymer composites. Engineering materials make use of powder PTFE as an additive in their compounds, since it significantly reduces wear and friction, making it popular for numerous applications like gears, bearings, and others, since it improves wear and friction performance and hence application durability. Additionally, PTFE powder is also used in industrial grease and oil lubricants to effectively reduce wear and friction under high load and high sliding speed conditions. Why this discussion about PTFE? Well, PTFE is a substance within a broader PFAS chemical group, of which some substances are linked to harmful health effects. PFAS, meaning per- and polyfluoroalkyl substances, comprise more than 10,000 chemicals. They all have in common the presence of a strong fluorocarbon bond in their molecules, which is one of the strongest organic chemical bonds in nature. Therefore, these bonds are difficult to break, and for its chemical stability, PFAS are known as forever chemicals. Being such a big and diverse group of chemicals, some of them can be harmful. For example, PFOA and PFOS are considered harmful and are already being restricted by global regulations already since many years. It is therefore likely that more PFAS constraints will follow soon due to ongoing activities at some regulative bodies. Although hazard properties of various PFAS substances may be different due to the nature of PFAS and the strong carbon-fluorine bonds they contain, PFAS molecules break down very slowly over time. Hence, we are confronting chemicals with very high persistence. That is why, again, they are so-called forever chemicals. Some can potentially be harmful to human health, but not only to human health, since PFAS can accumulate in the environment and in animal tissue. It is a fact that they have been found in drinking water, food, and even in the human body. And research shows that PFAS may lead to many chronic health problems in adults and children, including increased risk of many types of cancer, weaken the immune systems, or damage the liver, to mention a few examples. Consequently, future use of PFAS could be affected by emerging regulations and could potentially lead to a restriction or prohibition of PTFE. Today, there are activities among several regulative bodies opposing new laws and restricting PFAS in the future. We can follow activities in Europe led by the ECHA, and in the US, driven by the Environmental Protection Agency, and in Japan, driven by the Japan Ministry of Health and Labor and Welfare. But so far today, there are no market restrictions for the use of PTFE. Let's now focus on the activities in Europe. ECHA wants to ensure that PFAS are phased out unless they are proven essential for the society, and this would include possible restrictions for manufacturing, placing in the market, or the use of PFAS substances. As a result of the recent consultation period recently ended, that lasted 6 months and that ended in September 2023, in which was possible to submit exceptions, proposals, or voting votes, ECHA has received 600 comments. Following the screening of such a large number of comments received, ECHA is now clarifying the next steps for the proposal to restrict PFAS under REACH, the European Chemicals Regulation, and this may extend the initial timeline for implementation of the proposed restriction, which was originally set to Q3 2025. We can conclude then that although so far there are no market restrictions for the use of PTFE, if current proposals become widely accepted, they are expected to have significant consequences for the use of PTFE, not only in Europe, but globally. Clearly, materials containing PTFE as an additive will show poorer performance if PTFE is removed from their formulations. Worth to mention that a restriction of PTFE is not limited to plastics. Industrial greases and oil lubricants use PTFE as a thickener or as a lubricating agent, and that the removal of PTFE from their formulations is likely to lead to an inadequate application performance from a wear and friction perspective. Additionally, materials and lubrication should be looked as a system combination and not isolated, as in tribology applications, very often parts are operating under lubricated conditions, and performance is directly linked to the interaction between materials and lubricants. If PTFE is removed, frictional will become more relevant, generating frictional heat and compromising the application performance. So developing alternative solutions that can meet the required performance demands and reach application approvals can result in time-consuming and costly efforts. Therefore, there's an urgent need for PTFE-free high-performance materials, which should be able to compensate for the absence of PTFE, wear and friction modifiers, if both involves materials and industrial lubricants, always without compromising the application performance. PTFE-free materials should comply with some additional requirements apart from being PFAS or PTFE-free. Poor performance resulting from removal of PTFE could result in complex liability and reputation issues, not to mention cost impact derived from them. In this regard, it is highly competitive environment we are facing. Solutions should be cost-friendly. We can conclude by saying that there is a clear need for high temperature resistance materials that can deal with the high friction heat generated due to the removal of PTFE, and that they should have the ability to meet the tribology needs, including wear and tear, when paired with PFAS-free lubricating greases and oils. The good news is that there is a natural space for Stenil, Envalior polyamide 4.6, a high-temperature polyamide with an intrinsically outstanding wear and friction performance under high temperatures. At Envalior, we are committed and actively dedicating efforts to provide PTFE-free solutions in several work streams. Stenil polyamide 4.6 is a recognized product by the industry for its robust tribological behavior. It combines intrinsically high strength and ductility at elevated temperatures with very high wear resistance and low friction behavior without the need of additives, and can help achieving wear and friction performance needs also without PTFE. Important to mention that we are teaming up with leading lubricating manufacturers to bring out the best synergies from PTFE-free plastics and PTFE-free greases and oils. And with our decades of long track record in developing first-in-class materials for wear and friction applications, and with our expertise in tribology of plastics and our PTFE-free Stenil polyamide 4.6 product, together we can help our customers to find robust solutions for many tribology applications. Now I will hand over to Adnan.
Thank you, Marta. My name is Adnan Hasanovic, and I'm working in the application development at Envalior, focusing on tribology components, including gears, bearings, and other wear and friction parts. We are using indeed Stenil PA46 as one of our materials in these components, and Stenil is a material that helps meet performance, costs, and sustainability needs in tribological applications like this. When it comes to the sustainability aspect, we are using both PTFE and also PTFE-free grades in these applications, and we have been recently looking into the possibilities of using PTFE-free grades, the existing ones, and also new materials based on Stenil PA46 in applications like gears, bearings, and other wear and friction parts. On the next few pages, we will discuss briefly about each of these application spaces and also the Stenil material grades used in these applications, including the ones with but also without PTFE. Starting here with the timing systems and plastic chain guide components used in timing systems. So timing systems are used in automotive in order to regulate the valve timing of a combustion engine, and they are critical applications for a proper engine functioning, and especially for an efficient operation of the combustion engine. Now, in the timing systems, normally a chain or a belt runs against a plastic guide, which is used to tension the chain or belt, and the contact between the chain and the guide, or the chain or the belt between the guide, is generating friction. Now, in this type of application, every friction level that is generated is considered as the parasitic loss and basically affects the operating efficiency of the engine. So one of the clear goals in design and the material selection here is to minimize the friction that is developed in the system. We have been using over the past years several Stenil grades in applications in this application. This includes Stenil TW341, AGR2, and also AGR3W. And in this picture, we see an overview of the friction behavior as function of the chain speed of these three different grades. Now we see here a material which is designate in the blue the Stanil AGR3W, which is a PTFE grade, and despite the absence of PTFE, this is one of the materials that we indeed see very good performance in this application. Now we also see a material in green. This is a PTFE-based Stanil grades, which is also successfully used in this application, and the third material is designated with the yellow color. This is the standard PA46 with also PTFE-free and also performing sufficiently in many of these applications. Now, in addition to friction, also durability, performance, and wear resistance is relevant for components, for these components. And in this case, Stanil TW341 as well as Stanil TW441 are our most robust materials. So dependent on what the application needs most, either lowest possible friction or lowest possible wear resistance, there is choice here between 2 or 3 Stanil grades, which are all PTFE free and also working well from a wear and friction perspective in this application. Another important application space where we are using Stanil grades are actuator gears. This can involve various types of actuators used in automotives, but also gear applications used outside of automotive, for example, in domestic appliances. And also in gears, we use a combination of Stanil PTFE-free as well as Stanil PTFE-containing grades. Now, this can involve different type of gear designs ranging from spur gears to helical gears, planetary gears, worm gears, and also others. A third important application space where Stanil PA46 is used in wear and friction components includes sliding bearings. So these are general purpose components used in multiple end applications, for example, in transmissions and also in front-end accessory drive tensioners. Also in these applications, low levels of frictions are required, and especially low levels of wear resistance and long durability performance is required. Now, in case of sliding bearings, or bushings as we also call them, often PTFE modified materials are used to achieve the lowest possible friction and also the lowest possible wear resistance or the highest possible wear resistance performance. To understand better the performance of Stanil PTFE-free grades in gears, both the existing ones and also a couple of new development products, we have been performing tests in gears with these PTFE-free grades, including also with our PTFE-containing grades. On the left-hand side of this chart, we see a gear durability curve, which is basically indicating the torque as function of lifetime of the gears achieved in this test. So we do see here in total 6 materials, of which 3 are shown in green, and the green ones are the Stanil-based materials. Starting here with our standard material, which is not modified with any wear and friction agent, so doesn't include any PTFE, Stanil TW341, we see a certain level of performance. When we go to our PTFE modified material, we clearly see that the performance is better in the sense that more torque is possible at a given lifetime requirement. And we have a third material here, which is PTFE free, but wear and friction optimized, which is showing very interesting performance, even compared to our current existing PTFE modified Stanil material. So Stanil TW376 shows very promising performance here in gears, despite that it does not contain PTFE. In addition to the Stanil materials, we also have here 3 alternative materials, PA66, POM, and PPA, all of them containing PTFE. And based on behavior that we're observing here, we think that in some applications at least, these Stanil PTFE-free materials can also serve as potential alternative for some of the other materials based on PTFE, in particular PA66, POM, and PPA. On the right-hand side, we have a similar chart, which is referring to sliding bearings. So we have been observing here the wear rate, or measuring the wear resistance of a couple of grades and comparing that with each other. So we see wear rate on the vertical axis and the materials on the horizontal axis. Again, similar as in the gear durability charts, we do see that one of the grades, which is not containing any PTFE, but when friction modified, is showing very promising performance or behavior from the wear resistance point of view. So this is again the Stanil TW376, like shown on the other chart. So in summary, multiple Stanil PA46 based grades are available for tribology applications, including gears, bearings, and similar other OEM friction parts. This shows an overview of PTFE free materials. So on the unfilled or unreinforced side, we have several materials which are used in gears and bearings components, as well as in the timing system chain guides. And in the middle of this overview, we see fiber reinforced materials. So again, all of these are PTFE free, and we do have some of them which are modified with free and friction agents, but not based on PTFE. Now, in addition to this, to these grades, we are also continuously looking into options of developing and are currently working on new developments where PTFE is also substituted by other PFAS-free solutions, actually. However, in addition to these grades, we are looking to further explore the performance potential of Stanil PA46 in applications like this. So this brings me to the end of this presentation. I hope with this overview, we have been able to give you somewhat of an idea of how are we looking at the ongoing PFAS trends in the market, as well as how we are looking at the applications and especially the materials used in these applications, purely from a PFAS perspective. I hope you have been able to get some overview of what kind of materials we are currently using, which are PTFE free, and also that we are currently exploring the options to also develop new materials that hopefully further can enhance the performance in tribological applications like gears, bearings, and others. In addition to the materials, we also support these application spaces with design support, for example, CAE, as well as other application relevant support. We are globally present, so in case there is anything that you might have found interesting or might be relevant for you, in that case, please reach out to us and we will be looking to connect with you to discuss any details. Thank you for your time today. Goodbye.